In experiment 12, we're going to determine the molar solubility of potassium bitartrate in a couple of different solutions. And this experiment will take place in 5 different parts. First part, part A, you're going to prepare a saturated potassium bitartrate solution in pure water. We're going to measure out a specific amount of water. We're going to add a whole lot of potassium bitartrate to it, and we're going to stir it up, and it's going to dissolve. But all of the potassium bitartrate won't dissolve because we've actually put more solid into the solution than it's capable of dissolving. So what's going to happen is we're going to reach a saturated point, and therefore you're going to see some solid potassium bitartrate at the bottom of the container and a clear solution above it. This solution, because it's saturated, is in solution equilibrium, and what we're going to try to calculate is what is the concentration of the potassium bitartrate in that saturated solution. We're going to then, in part B, prepare a second saturated potassium bitartrate solution, but this time not in pure water. It's going to be in potassium chloride. And that's significant because potassium chloride will dissociate into potassium ions and chloride ions. So there's going to be potassium ions in this solution. And the potassium ions are what we call a common ion because potassium ions are in the formula of potassium bitartrate. So we're going to try to see what is the molar solubility of potassium bitartrate if we create a saturated solution, but there's already a common ion in that solution. In part B, there is one calculation you'll be required to do. You're going to actually measure out accurately the mass of the potassium chloride you're dissolving into the solution in part B. And from that mass, you're going to be able to calculate how many moles of potassium chloride dissolved. And by dividing by the volume, you'll calculate the molarity of the potassium chloride. And because it's a 1-to-1 ratio, that's going to equal the molarity of the potassium ions. So we're going to need to know what the molarity of the potassium ions are in part B. In part C, you're going to actually prepare a burette. And so this is just a technique that's been done before. Anytime you do titrations, you rinse a burette out with water, then you condition the burette with the standard solution that's going to go into it, and then you fill it up, make sure there's no air bubbles in the tip. So this will be part C, you preparing a burette with a standard sodium hydroxide solution, standard just meaning the solution is of known concentration. So with these 3 parts done, we're going to now move on to trying to determine the molar solubility of potassium bitartrate in these 2 different solutions we've created. The first one from part A, the solution of potassium bitartrate in pure water. Now, what's happening? When potassium bitartrate, whose formula is KHC4H4O6, dissolves in water, the potassium ion and the bitartrate ion separate from each other. And just for simplicity's sake, if I can abbreviate C4H4O6 with a T for tartrate, then I'm going to write the reaction that's occurring KHT solid turns into potassium ions plus bitartrate ions. So when you put a whole lot of solid potassium bitartrate in a given amount of water, the solid will dissolve into the ions. The ions will start to reform back the solid, and when the 2 reaction rates, forward and reverse, are equal to each other, we've reached solution equilibrium, and that's when you've maximized the amount of KHT that can dissolve in the water. And that maximum amount of a salt that can dissolve in water is called its molar solubility, so we're going to try to determine that. So because molar solubility is related to an equilibrium condition, if we can write an ice table, we can get some at least algebraic values for what's in the solution at equilibrium. If the original solution is just water, there won't be any potassium ions or bitartrate ions in there initially. But as the KHT dissolves, and the forward reaction has to be spontaneous because there are no products to turn back into reactants yet, we're going to form 1x of potassium, 1x of bitartrate, so the equilibrium molarities of the potassium ion and the bitartrate ion in our saturated solution will be x and x. Now, if you were to write something in the change line under the KHT, and we don't because it's a solid, but if you did, you would write a secret minus x there. What does that mean? That stands for the molarity of the KHT that's dissolving in water. And what do we define as the molarity of a salt that dissolves in water? That's its molar solubility. So if we can figure out this x value, that's the molar solubility. And the way we're going to do it is because that x value is the exact same as this x value, the molarity of the bitartrate ion. So why is that significant? Well, bitartrate happens to be an acidic ion. It has a hydrogen ion on it, and if it's acidic, that means it can react with a base. So we're going to take this saturated solution and we're going to add sodium hydroxide to it until we neutralize that acid. And that's the titration we're going to do in part D. So a titration involves a strong base being added to our saturated solution that contains this acid, this bitartrate ion. So the reaction will occur as we drip in the sodium hydroxide into the bitartrate solution. Is the hydroxide, being a strong base, will react completely with the bitartrate ions, pulling their hydrogens off, creating water molecules and then tartrate ions. I wrote a double-headed arrow here, but I should really write a single-headed arrow. Anytime you have a reaction involving a strong acid or a strong base, that's a reaction that goes to completion. So you're going to take a 25 milliliter sample of the saturated bitartrate solution, and we're going to try to figure out its molarity. If you titrate it with the sodium hydroxide solution to a phenolphthalein endpoint, which is going to be a color change that tells you when the solution goes from acidic to basic, so that's going to tell you exactly how much hydroxide it takes to neutralize the bitartrate. If we know the molarity of the standard solution and we know the volume it took, we can then calculate our X molarity in this equation. So let's say the standard sodium hydroxide solution had a molarity of 0.05. It'll be much more accurately given in lab today, but I'm just making this up for now. If we have 0.05 molar sodium hydroxide solution, then because there's one hydroxide in the formula, the hydroxide's molarity will be 0.05 also. And let's say to reach an equivalence point in this titration, it takes 15.0 milliliters. This is a stoichiometric problem. You try to find some reactant or product that you can convert the measured data into moles, and that's the colored data here for the hydroxide. If I multiply molarity times volume, that's going to give me moles of the hydroxide that were titrated. So 0.05 moles of hydroxide per liter multiplied by 0.0150 liters is going to give me the number of moles of hydroxide I titrated. And because now the second step, the mole ratio is a 1-to-1 ratio in the balanced equation, I can now convert moles of hydroxide into moles of bitartrate, and I now know how many moles of bitartrate must have been in my saturated solution. To get molarity, I now have to divide by volume. So if I divide by 0.02500 liters, I now have the moles of bitartrate per liter, and I come out with 0.03 molar of bitartrate. Why is that significant? Because that was X in our ICE table from before. And remember, X also stood for the molar solubility. So therefore, we've calculated that the molar solubility of potassium bitartrate in pure water from these fictitious numbers here would be 0.03 molar. Now, you're also in part D going to be asked to calculate the KSP for potassium bitartrate. So we do have to write the KSP reaction. To calculate a KSP, the reaction is the solid salt dissociating into its constituent ions. Not a stoichiometric problem, not a reaction that goes to completion. This is an equilibrium problem. So we're going to write an ICE table for this. So initially in pure water, we don't have any potassium ions or any bitartrate ions. When the reaction proceeds in the forward direction, we'll form X molar of potassium ions, X molar of bitartrate ions, and then at equilibrium, we'll have X molar of each of those. Now, the X value that we would secretly write under KHT solid would be minus X. That stands for the molar solubility. And we actually know what the molar solubility is because earlier in part D from the titration, we calculated it. The molar solubility was 0.03 molar. So that's our secret way of getting X, because the KSP now would just be the concentration of potassium ions multiplied by the concentration of bitartrate ions. Well, that's going to be X times X. And so seeing how we already know what X is, we can multiply those numbers together. And so we would predict that the KSP for the potassium bitartrate would be 0.0009. So that's calculating the molar solubility in the saturated solution in pure water, and then the KSP for the salt based upon that. Next, what we're going to do is we're going to try to determine the molar solubility of the potassium bitartrate in the saturated potassium bitartrate solution in KCl. So when the potassium bitartrate's dissolving, same thing happens. It just dissociates into its constituent ions. And I'm going to, once again, abbreviate the tartrate ion with a T. Now, though, because the solution already has potassium ions in it, when you write your initial line, you don't write 0 on 0. you will have calculated in part B what the molarity of the potassium ions are in the solution. I'm going to make up a number for me, 0.10. Yours will be something different. And even though we have an amount of potassium ions already in the solution, because there are no bitartrate ions, once again, the forward reaction has to be spontaneous. So when you put a bunch of solid KHT into the water and stir it up, it will dissolve. And you'll form X amount of potassium ions and X amount of bitartrate ions. So at equilibrium, we'll now have 0.10 plus X and X. How is this going to help us get the molar solubility? Because once again, that secret minus X there stands for the molar solubility. So if you want to calculate what X is, we can once again do a titration because the molar solubility will exactly equal the concentration of the bitartrate ion. And that bitartrate ion is an acid, so we can titrate it with the sodium hydroxide to determine its concentration. So let's talk about an example calculation of that. To titrate the saturated potassium bitartrate solution that already has the KCl in it, it's going to be the same reaction. The sodium hydroxide will only react with the acidic part of the solution, which is the bitartrate ions, forming the tartrate ion and water. So we're going to once again pipette 25 milliliter sample. We're going to try to find the molarity of the bitartrate ions. The sodium hydroxide being a standard solution, I'm assuming it stays 0.05 molar, and the hydroxide concentration will still be 0.05 molar as well. If we do the titration, this is going to take a different volume. Let's say it takes 4.0 milliliters. So now let's solve for the molarity of the bitartrate ions in this solution. So I'm going to take my molarity and volume and multiply them together to cancel out the liters to give me the moles of hydroxides that had to be used in the titration to reach the equivalence point. Second, the mole ratio, 1 to 1. 1 mole of hydroxide on the bottom, 1 mole of bitartrate on the top, so the moles of hydroxide cancel out. And now that we have moles of bitartrate, if I divide it by the volume, that's going to give me the molarity of the bitartrate ion in my saturated solution, and this comes out 0.008. And if that's the concentration of the bitartrate ions, that's also the molar solubility, so we would say that in this solution that already contained a common ion, the potassium ions, the molar solubility is 0.008 molar, which is significantly smaller than what it was in pure water. Why might that be? If you think about the equilibrium that exists in a saturated solution, if you put in a whole bunch of potassium ions into that solution, notice where the potassium ions are. They're on the right side of the equation. If you increase the amount of a product, which way does the equilibrium shift? Has to shift to the left to get rid of those excess ions. If it shifts to the left, going to the left means the ions are turning into a solid, so you create more solid, which means you have less ions dissolved. The molar solubility should be lower, so let's hope that's what you see today. Now, you'll also be asked to calculate the KSP of the potassium bitartrate from this solution as well, and a solubility product constant is a constant because it doesn't change unless you change the temperature, right? From our last test, that's the only thing that'll change the numerical value of an equilibrium constant. So even though this solution had a bunch of chloride in it, or potassium ions in it rather to start, we should still be able to calculate the same KSP, and so you're going to see if that actually does work out. So here, from our solution that had the saturated bitartrate with KCl, we were starting with a solution that was 0.10 molar in potassium ions. The reactions proceed spontaneously to the right, so we form X of each of the two products. And so the equilibrium molarities will be 0.10 plus X and then X. And keeping in mind that secretly X does stand for the molar solubility, we actually have that answer from above. In this solution, the molar solubility is 0.008. So if that's the molar solubility, and we want to try to calculate the KSP for the potassium ion concentration, it's 0.10 plus 0.008. And then for the bitartrate ion, it's 0.008. And if we multiply those together, that gives us a KSP of 0.0009, which for my work worked out really well. That's the exact same number. We'll see if you come up with the same thing when you do that in lab today. Now, in the post lab, I'm going to give you a couple of questions. I'm going to give you the actual KSP for the potassium bitartrate. I'm going to ask you to calculate theoretically what the molar solubility should be, a typical type of calculation you do with solubility product constants. So in the pure water, what you're going to do is you're going to assume that there are no potassium ions or bitartrate ions in regular old water, so they're going to be 0 and 0. The reaction proceeds spontaneously to the right, and so at equilibrium, we're going to have X molarity of the potassium ions and the bitartrate ions. Remembering that X stands for the molar solubility, if we can solve for X, then we'll know what the theoretical molar solubility is. The KSP expression is potassium ions times bitartrate ions, and in the post lab, I've told you that it's been looked up, and the KSP for potassium bitartrate is 6.8 times 10 to the minus fourth. So therefore, 6.8 times 10 to the minus fourth must equal X squared, and you should be able to solve for X, which will be the molar solubility in pure water, and we'll see how close that value is to what you got in part D today. Then they'll also ask you to determine what the molar solubility would be theoretically in the solution that already contained the potassium ions. So remembering from part B, the solution contains some known amount of potassium ions. Reactions proceed spontaneously to the right. Equilibrium molarities will be this. KSP expression is going to allow us to calculate what the KSP is, and we're going to actually know, we're going to use the KSP expression to calculate the molar solubility because we're just going to try to solve for X. If we know the KSP is 6.8 times 10 to the minus fourth, then 6.8 times 10 to the minus fourth would have to equal 0.10 plus X multiplied by X. And if you can solve this for X, that's going to be the molar solubility of the potassium bitartrate in this solution that has a common ion. And we'll see how that answer matches to what you got in part E.